Okay guys, back to our analysis of a coordination compound, specifically spectrophotometric testing for copper. So we left off having discussed how you're going to make your standard solutions. Now we're going to talk about actually measuring their absorbance. I'm not going to show you the setup with the computer and the software. I think it's better demonstrated in class, so UTAs will be helping you with that. Hopefully we can achieve doing those demonstrations in a socially distanced manner. We have plenty of the spectrometers around, so that shouldn't be a problem. So I just wanted to show you what spectrometer looks like and describe in general what it is and how it's used in the laboratory. So this little black box that doesn't look particularly impressive is actually a very interesting device which provides a lot of information to us in terms of characteristics of some solutions we commonly encounter in the chemistry lab. So basically, if I could lift the cover and show you the inside of it, right here where the little white sun-like icon is, you would see a little light source. It's basically a special light bulb. This here is a compartment where your sample will go, and then you see these lines here, so light will travel through the sample from the light source through the sample to the light detector. So light detector somewhere over here. Light detector will look at how much light came out of the sample compared to how much light came in. The sample compartment is very important because it houses a special container called a cuvette in which analyzed solution is placed. The cuvette looks like this. It's a small rectangular plastic device. Each of you will get at least one of these. You will place your solution into the cuvette up to the fill line. There's a fill line right there. Now, I'm not sure if you can actually see it in this video, but the cuvette has two sides that are clear and two sides that are opaque. I actually didn't do a very good job picking out the cuvette. It's kind of a dirty one. If you notice any specks or spots on it, it will have to be thoroughly rinsed before you use it, especially on the clear side. So you typically handle the cuvette by the opaque sides, like this. So these are opaque sides, so I didn't hold it correctly. And then the clear sides is where light will be going through. Once again, the fill line is right there. So you'll place your solution using a pipette or an eyedropper into the cuvette. You will then calibrate the spectrometer. We'll show you the procedure for calibration in class. I would just point out that detailed instructions on how to use the spectrometer are provided in your lab manual on page 92, so be sure to look it over before coming to class for this experiment. And then it's important to place the cuvette into the spectrometer correctly, meaning you will always be putting the cuvette in such a way where the clear side will be the one facing light. So this is the clear side, so I want to place it in the spectrometer like this and push it in. So clear side should be perpendicular to light direction. The light direction is shown by these lines. So you want to make sure you handle the cuvette by opaque sides and you place the cuvette in the spectrometer in a way where clear side is the one facing the light, and be sure to push it in. And from there you'll be working with a laptop attached to the spectrometer, which will be running special software and will allow you to measure absorbance. And then once absorbance reading is provided by the software, you'll be able to record it onto data sheet number 2. A little bit about data sheet number 2. Data sheet number 2 is where you'll record all your information regarding testing for copper. And one thing that you will find on data sheet 2 is a table that will list 5 solutions, their concentration, and their respective absorbance. It says absorbance is at 620 nanometers, and concentration of copper ion in stock solution will be 0.20 moles per liter. There's 5 solutions in total. 1 is undiluted stock, and 2, 3, 4, and 5 are the standards you'll have to prepare during the previous experiment and save in sealed large test tubes in your drawer. So when you come in, you'll go right to measuring. Now what I'm hoping we can do is we can have stock solution. We'll ask your TA to measure it, so they'll tell you what the absorbance is, just to save precious lab time, because we do have to squeeze in as much experimental work as possible under these conditions. And then the remaining 4 standards, what I'd like to happen is one partner will measure 2 and 3, and the other partner will measure 4 and 5. You cannot work together, but you can take turns measuring, and then you can just exchange information, keeping 6 feet apart, of course, as to what the absorbance values of these 4 solutions that you obtained were. I'd like to point out that ideally all 5 solutions absorbances should be measured using the same spectrometer. So we will work on how to make this happen for you in the lab, so you can get these values in a minimal amount of time, even in the conditions when you can't really work together. And then once you got that done, you move right to analysis of the synthesized product for copper ion content. So here, part 2 is where you will actually be testing your purple carbonation compound that you'll have in the vial. So for this procedure, you'll be asked to measure a portion of this compound weighing close to 1.3 grams, I believe your procedure calls for. Again, it's just a recommended amount. You don't have to have an exact amount. Anywhere close to that is fine. You'll record the exact amount you weighed on to data sheet 2 to the nearest milligram. So remember, significant figures, very important. And then this amount will be placed in a small 50 milliliter beaker. You will then take this beaker to the hood where a hot plate will be set up by your TA, and you will gently heat the solid, no liquid added, until it starts changing color. Now, why would it be changing color when heated without any liquid or any other chemical added? Well, this compound, this purple material, tetramine copper sulfate monohydrate, we talked about this, the presumed formula for it. It contains these 4 ammonia molecules here, and these ammonia molecules are coordinated or bound loosely to the copper ion. So when you begin heating this solid, the ammonia molecules are going to be breaking off, and this is why we want you to do this in the hood, so you don't have to smell the ammonia vapors that will be generated. And when this happens, the water molecules from the air, we have plenty of those around, will replace ammonia. And guess what? You're going to get this substance here, which was your starting material for synthesis. So this heating will be accompanied by a color change from purple to light blue. When you're heating, you have to stir it, the contents of the beaker carefully with clean, dry stirring rod. And when you notice that most of this purple substance has turned blue, you can stop heating. If a little bit of purple specks still remain, that's okay. You will then let the beaker cool after carefully taking it off the hot plate using hot mat. And then you will add some water to it. At this point, and some hydrochloric acid. Hydrochloric acid, being a strong acid, will be able to neutralize any ammonia remaining, so the color of your solution will be bluish green. It won't be completely blue, it will have a green tint. It sort of looks like seawater. The green color is due to interaction between chloride ions from HCl with copper ions, and it's perfectly normal. The main thing to ensure, and you probably want to either talk to me or one of the TAs if you notice there's any solid or any cloudiness still present. This may require some additional HCl to be added. So once you added water and HCl and completely dissolved your solid, so clear solution results, it won't be colorless, it will be greenish blue, but it has to be completely clear. You will then transfer the solution into what's called a volumetric flask. This is specifically a 100 milliliter volumetric flask. Volumetric flasks are very important in chemistry. It's an extremely important skill for you to have to know how to work with volumetric glassware in the lab. You will need these skills when you progress to more advanced courses, and I consider skill of properly using volumetric flasks a critical skill. So you're going to transfer your green solution into this flask, rinse the beaker a couple of times with a little bit of deionized water, and pour the rinses into the flask. This ensures that the original solution is completely transferred. And then you carefully will add deionized water to the flask. When you first begin adding water to this flask, you'll notice color changing from green to blue, like it's supposed to. And then the thing to worry about is this mark right here on the neck of the flask. You should not go over this mark. People have sometimes sort of disregard for instructors' recommendations, I guess, and they think it's not that important, and they start adding water too quickly, and guess what? They quickly go over. If the flask is filled over this mark, solution is considered to be prepared incorrectly because you don't know what the volume is. So what you want to do is, when you get into the narrow neck, slow down adding water and don't add it directly from the faucet, because I guarantee you'll go over. Instead, take your wash bottle or a pipette or a eyedropper and start adding water drop-wise. The best thing to do, the most accurate way, is to set the flask down. Make sure your eyes are aligned with the level you're reading. So lower your head and carefully add water drop by drop. Correctly added liquid or correctly filled flask would mean that the bottom of the meniscus of the liquid is right where meniscus is. At the bottom of the meniscus should be right on the line, not any higher. If you go over, quickly pipetting extra water out will not help because copper will already have dissolved in that water. Once you've added water to the mark, and the bottom of the meniscus is sitting right on this etched mark, you'll get a piece of parafilm. Your TA will show you how to seal the flask with parafilm tightly. You'll invert the flask at least 10 times to mix the contents. This solution is going to be your unknown, meaning you don't know the concentration of copper in it. But you'll know that all the copper in this solution will have come from a portion of this purple material. And so by measuring absorbance of this solution and using the calibration graph prepared using data from your standards, you'll be able to find concentration of copper in this solution and relate it to mass of copper and then mass percent copper in the purple compound. So once the solution is prepared, one quick but very important measurement to be made is measuring absorbance of this solution in a manner very similar to the method you use to find absorbance of your standards. Make sure you measure absorbance of this solution using the same spectrometer as you use for your standards measurements. Next, I'd like to briefly talk about the calibration graph you'll have to prepare. So if you recall, the Beer's law that we mentioned earlier looks like this. And you can see its direct proportional relationship between absorbance, A, and molar concentration of the substance we're interested in our case, copper. So what kind of equation or what kind of graph, should it be? Well, hopefully you see that this is a direct proportional relationship, so we expect a linear graph. So what you'll want to do is you'll go to Excel, Microsoft Excel. You're going to first enter your data into the spreadsheet. Concentration here is independent variable, while absorbance here is your dependent variable. So you will want to make sure you place your parameters into the spreadsheet correctly. By default, always, the independent variable goes on the left, while dependent variable goes on the right. So make sure concentration values are on the left and absorbance are on the right. It is important because this is the only way to make sure your graph will be prepared correctly. You will have a total of 5 values in each column because you'll have 5 concentrations and 5 related absorbances. Why 5? Because you have stock, that's your number 1 solution, and then 4 additional standards for a total of 5. Then you're going to make a scatter plot. And then you're going to get linear trend line. This is very important. Not line graph, instead it should be scatter plot with linear trend line. You'll notice that in Beer's law, there is no y-intercept, so if we compare this to the equation of linear relationship from math, this is how linear relationship in math typically looks like. This is your independent variable x, this is your dependent variable y. This, of course, is proportionality coefficient, which translates into the slope. And b here is typically referred to as y-intercept. In Beer's law, there is no y-intercept, which means you need to set y-intercept to 0. And so when you look at your graph, this will have your absorbance, this will have your concentration of copper. Make sure to label the axes, and for concentration you must include units, it's moles per liter. Absorbance is a rare example of a parameter that's unitless, so you don't need any units here. And then you will have your scatter plot, which should basically be approximated by a linear trend line with a positive slope. The greater the concentration, the greater the absorbance. And so it should be something like this. Y-intercept should be 0, and then should be set to 0. The graph does not have to start at 0, just y-intercept should be set to 0. And then you're going to get the equation of the line. The computer can do that for you if you just click one little box. And then once you have the equation of the line, it will be y, certain numerical parameter for slope, and then x. So y is your absorbance and x is your concentration. Once you have the absorbance value for your unknown, that solution you make in the volumetric flask, you'll measure its absorbance. You will then use the equation of the line to find concentration. I hope you understand you will have to plug absorbance in for y and solve for x. Make sure to show all work how you find concentration using absorbance by plugging absorbance into y and solving for x using the equation of the line given to you by the computer software. And then once you know the concentration of copper in the unknown solution, you'll be able to find mass of copper in grams. And then finally, mass percent copper in the purple carbonation compound. Now, this portion of calculations from concentration of copper to mass and from mass of copper to mass percent, I did provide you with all the necessary information to do these calculations correctly. No need to invent a wheel. So if you look at page 91 of your lab manual, there's a special section there, right under the procedure which we just discussed, that says calculations. And you see I gave you the equation for mass of copper. It starts with concentration of copper. Now, I hope you understand that this concentration of copper is concentration in this unknown solution you'll have prepared in this flask. And this concentration of copper must be obtained from the equation of the line of your calibration graph. There is no way to find this concentration of copper unless you've prepared the graph and you found the concentration from the absorbance by using the equation of the graph. So this concentration comes from analyzing the graph, and then you can see how you can find mass of copper. Finally, mass percent copper is found as mass of copper and it says here divided by mass of sample taken for analysis. I would like to warn you that a very common mistake is when people are looking at this equation are not really sure what to use for mass of sample taken for analysis, and they end up plugging in the value of their actual yield or whatever total mass of the purple compound they got. But it is not correct, because the unknown solution is not prepared from the entire sample of the purple compound you were able to obtain during synthesis. Instead, this unknown solution in this flask is prepared from a portion of the coordination compound that you will have weighed in the beginning, and it should be something close to 1.3 grams. So make sure you use proper number here for mass of sample taken for analysis. This mass of sample taken for analysis is the mass of purple compound used to prepare the unknown solution. I hope this introduction is helpful and you'll be able to successfully complete this procedure.